so for question number 2, continuing on from yesterday, okay, we have a ball that's moving up a hill with an initial velocity of 3 meters per second. So VI is going to be positive 3.0 meters per second, okay, where positive is going to be up the hill. 4 seconds later, okay, here's a major error with the way this question is written. How many significant digits does the word for have? I have no idea. That's why you never write measured values as words. Okay? It's just dumb. Okay? And there's no way that that should have ever gotten by the checkers for that book. But it did. Okay? So we're just going to say that the time here was 4.0 seconds because nobody writes it F-O-U-R. Okay? No. All right. So we got T, and we also know that a little while later it's moving down the hill at 9 meters per second. So this is the key to getting this question right, is recognizing VI and VF are in opposite directions. Okay? We are looking for the displacement of the ball, okay, from its point of release. All right. The only formula I have that would have these things in it would be this one. D equals VF plus VI over 2 times T. Okay, that's the one that will calculate displacement with the information that I have. All right, so now I'm going to add those. I'm going to put those in because I don't have to manipulate. I just have to plug in the numbers. And I'm going to have negative 9 plus 3, okay, positive 3 divided by 2, and then multiply that by 4 seconds. Okay, so negative 9 plus 3 is going to be negative 6. Are we okay with that? Negative 6 divided by 2 is negative 3. Negative 3 times 4 is? Okay, should I leave my answer as negative 12 meters? No. What direction did they give me? Down. Uphill and downhill. Now, this is going to seem really picky. Uphill is different than up. Okay, so if you're given uphill, make sure your answer is uphill, not up. Up is straight up. Okay. So I'm just going to say 12 meters downhill. Okay, I would not write negative 12 meters uphill. While that's correct, it sounds weird. Okay. All right, so is that ringing a bell for that formula from yesterday? Okay, so we still have a few more formulas to get through here, okay, that we haven't touched on yet. So I want you to write this one, okay? Write this one down. This will be our example of our next acceleration formula that we'll be using. Okay, so again, reading through the question is really important so that we can figure out what givens the question is offering. Okay, so a golf ball is initially traveling at 25 meters per second. So VI is 25 meters per second. It hits a sand trap and slows down with an acceleration of negative 20 meters per second squared. Okay, so it gave me acceleration. Right? Find its displacement after 2 seconds. Okay, so I have VI, A, and T, and I'm looking for D. All right, so the only formula I have that has those pieces of information in it is this one. Okay, D equals VI times T plus 1/2 AT squared. Basically that formula that calculates the area under the line on a velocity versus time graph. Okay, so I don't have to manipulate this one, I just need to plug in the numbers. Okay, VI was 25, okay, times 2 seconds, plus 1/2 times negative 20, and it's really important that you remember to put the negative in here, or it'll say that the ball goes faster after hitting the trap, okay, times the time again squared. All right, so there's my numbers plugged in. Okay, so we got 25 times 2 plus 0.5 times negative 20 times 4. All right, so we're looking at a displacement of 10 meters. And I would assume that we would say that's forward. Okay? could also say positive. They don't really do a good job of giving us directions in this question. I want to follow that one. Okay, manipulation of this formula. It can be a little bit tricky. Okay, so let's have a look at the manipulation here. So D equals VI times T plus 1/2 AT squared. Okay. How do I manipulate this if I want to solve for VI? What am I going to subtract? You bet. I'm going to subtract this whole thing over to this side. Okay, that'll isolate the VI times T. All right, so D minus 1/2 AT squared equals VI times T. All right, how do I get VI by itself? Okay, divide both sides by T. All right, when I do that, do these T's cancel? No, they don't. Okay, they don't because there's a subtraction operation up here. If all of these numbers were being multiplied, then yes, I could cancel the T's, but because there's a subtraction operation there, I can't. Okay, so that's the manipulation for VI. All right, now I want to solve for A. What should I move first?
VRT.
Right, how will I move it?
You subtract.
Exactly. So D minus VI times T equals 1/2 AT squared. All right, how do I get A by itself? Right.
Divide the left side by 2 T squared.
Right. Okay, I just divide both sides by 1/2 of T squared. Okay, comes over here, and I'm solving for A. Okay, so there's a little bit of tricky stuff in that one for manipulation. Now the really tricky part. Solving for T. T's in two places. That sucks. Okay? So, luckily for you, we can't guarantee that you've taken this course before having taken Math 20, where you would learn how to factor this and isolate T. Okay? So, you won't have to isolate T unless VI is 0. Okay? The reason you can isolate T if VI is 0 is because if VI is 0, what's VI times T? 0. And then this becomes D equals 1/2 AT squared, and isolating T is quite simple from there. Okay? You wouldn't have to use the F word factoring for this after that. Okay? So I won't ever ask you one where you actually have to solve for T if there was a value for VI. Okay, it says right in the curriculum I don't have to do that. So I shan't. Okay? All right. Everybody okay with the manipulations for that formula? Okay. So let's have you guys try these two. Neither one of them requires you to solve for T. Okay? But you're using that formula. Watch out in question number 2, because once again they're messing around with non-matching units. Okay, so you'll have to do a little bit of conversion to get everything into meters and seconds. All right, so we don't actually have to manipulate for either one. Okay, they both ask for the displacement. Okay, so for question number 1 here, okay, we've got moving down a uniform slope at 3 meters per second. Okay, so VI will be 3.0 meters per second. Okay, the acceleration down the hill is 4 meters per second squared. Okay, and we're looking for the displacement after 5 seconds. Okay, since everything is down the hill, I'm not going to bother putting plus or minus or anything on there. All I have to do is plug in my numbers to D equals VI times T plus 1/2 AT squared. Okay, so we've got 3 times 5 plus 1/2 times 4 times 5 squared. Okay, when we do that, we should get 65 meters, not down, but down the slope or down the hill or something like that, because down would imply it's falling through the slope somehow. Okay. All right, for question number 2, again, the key here is that we have to figure out what our meters per second and seconds are, right? So we have an initial velocity here of 100 kilometers per hour, which when we divide it by 3.6, Okay, we're looking at 27.7 repeating meters per second. Okay, and that's going to be a positive value. Okay, on a flat road, they apply the brakes at 0.8 meters per second. What do I have to put in front of that? It's negative, right? Meters per second squared, and they do that for 1 minute, which is 60 seconds. Okay, and we're looking for, again, how far did they travel during that time. We don't have to manipulate, just plug in our numbers. So 27.7 times 60 plus 1/2 times negative 0.8, and it's crucial that you remember to put the negative in there, times 60 squared, right? And when we do that, we should get 2.3 times 10 to the 2 meters as the displacement in a forward direction on that one. Okay. All right, questions on that formula? Okay, so we still got a couple more to get through, 2 more. All right, so I want you to write this one down. Okay, we have a speedboat that is slowing down at 5 meters per second squared and comes to a stop. Okay, the process takes 15 seconds. We're looking for the displacement of the boat. Okay, so for this question here, okay, we've got, they give us the rate of acceleration, and that acceleration is negative. Okay, and this would have been a fairly uncomfortable acceleration. Okay, like 5 meters per second squared is more than half of the acceleration due to gravity. Had you not been belted in, you would have flown forwards, okay, in this boat. Okay, so that's our acceleration there, okay, and it comes to a stop. So VF is 0 meters per second, okay, the process takes 15 seconds, okay, we're looking for the displacement of the boat. All right, so those are our givens, which means now we're using the counterpart to the formula we just used a minute ago, VFT minus 1/2 AT squared. Okay. Now, in this case, again, I don't need to manipulate it. I'm just solving for D, so I just plug in my numbers. Okay, what's 0 times anything? Okay, so I'm going to have 0 minus 1/2 times -5, okay, times the time, which was 15 seconds. Okay, so again, it's still important to keep this 0 here in this one because I'm subtracting, and I'm going to be subtracting a negative number, which is going to give me a positive number, which makes sense. I'm slowing down, but I'm still moving forwards. Okay, I'm slowing down, but I'm still moving forwards. Okay, so we're going to have 0 minus 0.5 times -5 times 15 squared. Okay, so we're going to have that this thing is going to travel 562.5 meters, but we only have 2 significant figures, so 5.6 times 10 to the 2 meters, and that would be forward. It just says find the displacement, so we have to say forward on that. Okay, now manipulation of this formula, very similar to the manipulation of the other formula. All right, so when it's initially set up, okay, if I want to solve for VF, what do I do with the 1/2 AT squared? I would add it over to the other side, so I'll have D plus 1/2 AT squared equals VF times T, and then I would divide both sides by T. That would leave me with VF. Okay. If I was looking to solve for acceleration, then I would do something a little different. I'm still going to add this over to the other side, okay? But I'm only doing that so that I get a positive number here. Okay, so I eliminate this negative. I'm going to go D plus 1/2 AT squared equals VF times T. Okay, and then I'm going to subtract the D back over here. Okay, and then I'm going to divide by 1/2 of T squared. You don't necessarily have to do it that way, but I do so that I don't mess up my signs. Okay? If I don't do it that way, I find I forget that I've got a negative in there, and then I end up with the wrong direction on the answer. All right. Questions on that one? Okay. Let's have you guys try those two. They both involve that formula. Okay. Sorry. I take it back. No, I don't. You can do both. Okay. You can do both because in question number 1, VF will be 0. Yes. So for our first problem here, I don't know if anyone's ever seen when a plane lands on an aircraft carrier. It's a pretty violent stopping action. Okay, there's basically cables that go across the deck of an aircraft carrier and a hook that hangs out the bottom of the plane. Plane lands on the aircraft carrier, the hook catches the cable and yanks the plane to a stop because no plane could possibly land on the short distance that the surface of an aircraft carrier provides. So they actually have to be arrested with these cables. Okay, in the same way they have to be launched with a big catapult. So we've got this aircraft carrier that is going to bring the plane to a stop. So we know that VF is 0 meters per second. It's going to do that in a displacement of 150 meters, okay, with an acceleration of negative 15 meters per second squared. Right? So like it would give you whiplash. Okay? Well, the opposite of it because you go forward instead of backward. Okay? It'd be a lot. So we're looking for the time of the plane to stop. Okay, the formula we have to use here is VF times T minus 1/2 AT squared. Okay, now the thing we have to remember is that since VF is 0, okay, I can effectively do this and eliminate that second T from the formula, okay, by just making that 0. Right? So now I want to get the T squared by itself. Okay, so I'm just going to get rid of the 0 as well here, okay, and isolate T by dividing both sides by negative 1/2 times A, and then doing what? Square rooting, right, because T is squared. All right, so T will equal then, for this one, the square root of 150 divided by negative 1/2 times negative 15. If you don't keep track of the negatives, your calculator will have a conniption fit because you'll be trying to take the square root of a negative number, which is impossible. Okay? Yeah, so you just have to make sure you're watching all of your negatives. Okay? And so what we end up with here is the square root of 150 divided by negative 0.5 times negative 15. All right, so we're looking at that this would take 4.5 seconds. All right, this is what they've got there. All right, how many people have done number 2? Okay, let's have a look at that one too then. Okay, so the 1968 Corvette took 6.2 seconds to be accelerated to 160 kilometers per hour. That's 100 miles an hour, okay? It's fast. And only took 6.2 seconds to get there. All right, so we know that the time is 6.2 seconds. Okay, we are looking for its acceleration. Okay, we know that the final velocity is 160 kilometers per hour, but I need that to be in meters per second. All right, so we're looking at 44.4 meters per second. Okay, and it does that over 220 meters. All right, so that's the information we have. Okay, again, D equals VF times T minus 1/2 AT squared. Right. So what I would do is bring the half AT squared over by adding it. Right. So I'm going to have D plus 1/2 AT squared equals VF times T. Then I'm going to subtract D over to this side, and then I will divide by 1/2 of T squared, leaving A on this side. Okay, and then I will plug in my numbers. So I have 44.4 times, what's the time? 6.2 seconds. Okay, minus 220, okay, divided by 1/2 times 6.2 squared. Okay, and when we do that, we should get 2.9 meters per second squared. All right, we still have one acceleration formula to cover. We'll be covering that one tomorrow. Okay.